Worksheet 3, number 16, parallelogram problem. A very good idea. Come on in.
I was just going to tell them about how you...
Worksheet 3, parallelogram. Again, we just mentioned that it would probably be very wise to know the parallelogram problem for the test on Friday. All right, a large park in the shape of a parallelogram. We remember what a parallelogram looks like, right?
No.
Really? Okay. Well, let's see. The first however many letters of parallelogram is parallel. Does that look familiar? Okay. Do you remember what it's called if all the sides were equal in length? While we're doing our geometry review here? Well, it would be equilateral, but there's a special name for an equilateral parallelogram. It would be a rhombus, yes. But equilateral just means equal sides, so you could have an equilateral parallelogram. It would just be a rhombus. Now, I don't know that would be as much fun as a non-equilateral parallelogram. So we got our parallelogram, diagonal paths that meet at a 60-degree angle. So let's draw some diagonals. At a 60-degree angle. Now it doesn't tell me which one's 60, but one of these is acute and one of these is obtuse, right? One's less than 90, one's more than 90. So the less than 90 one's got to be the 60. So JD, you get the easy question. I think an easy question. What's this angle then?
30. No. 120.
120. A lot of geometry review going on. The diagonal paths are 12 kilometers and 20 kilometers long. Well, again, it doesn't tell us which one's which, but I think I can tell by looking that one of these is long and one of these is short. So let's make the short one 12 and the long one 20. Although it's 12 all the way across, and I think I want to just be doing a one of these triangles. So if the whole thing is 12, then this is 6, and this is 10. Does that make sense?
Would it matter if you switched them up?
You know what? I don't think it would matter. I think you would still get all the right answers if you put them on the wrong one, even if you did the angles wrong. Like your picture would be kind of out of whack, but I think you'd still get all the right answers because you're still going to get two different side lengths that you'll just need to add up to get the perimeter. So I think you're right. Even if you put them in the wrong spot, you'd still be okay. So perimeter, I need all the outsides. This is another one of those two triangle problems. Let's see. I guess we can call it, well, that's not really length and width. Let's just go A and B. So I'll need to find A, and I'll need to find B. And let's plan ahead here. How am I going to find, or what will the perimeter be once I know A and B?
2.
Yeah, just making sure we get 2 of each of them. So the perimeter will be 2A plus 2B when we find A and B. All right, well now we sort of turned this from a parallelogram problem into a triangle problem. So we can ignore, everything but that green triangle. And I need to find A. Danny, what should I use to find A?
X squared equals
Yeah?
10 squared plus 6 squared minus 2 times 6 cosine of 4.
Nice. I was really just hoping you'd say law of cosines, but you gave me the full answer. that is law of cosines. The A and the 120 are across from each other in the triangle, so they need to be across from each other in the equation. Again, not given that one, but hopefully we've used it enough where you've got it. So let's find A. Again, take the time in class right now to make sure you can put that in the calculator. Don't be the guy that on test day doesn't know where the squared button is. You laugh. There's always one or two, I guess I can't officially say they're dumb questions, but questions that students should know the answer to, put it that way. 10 squared plus 6 squared minus 2, 10, 6, cosine of 120. Better check my radian degree. 196, that seems a little large for the problem. Square root of that, which is a perfect square. So A is 14. And then I need B. So now everybody got A in their calculator. Cecilia, how am I going to find B? Just go ahead and give me the equation.
Okay. It's going to be 10 squared and then 6 plus 6 squared minus the 2 and then 10, 6 and then cosine of 60.
And what does that equal?
B squared.
B squared. Good. So it's really similar, but that makes sense because lots of the stuff is the same. That angle is different, so make sure we use 60 across from the B. And I guess if I was really smart, I could go get that entry in my calculator and just change the 120 to 60. Again, be careful. That's I need to square root that. And then I need 2 of each of them. So times 2 plus 2 times 14, 45.436. The perimeter, the distance around. Okay, so parallelogram. We hadn't done a parallelogram. You probably haven't done a parallelogram in years, literally years. What did we need to know? I guess we need to know what it looked like. We need to know what diagonal is. And we needed to know that 60 was one of the angles. And like Danny said, even if you put it in the wrong spot, you'd get 120 for the other. Your picture might look a little wonky, but you'd still get all the right answers. And then I guess the last thing is those diagonals intersect each other or bisect each other, cut each other in half. So be careful. It gave you 12 and 20, but that's not really the numbers we used. Questions on that? Part B, find the area of the park in square kilometers. Right. I think there's several ways to do this. Any ideas on how to find the area of the park?
I'm going to find the area of the 2 different triangles and then multiply each by 2.
I think that's probably the most straightforward way. She said find the area of the green one and the orange one, multiply them each by 2 because there's 2 green ones and 2 orange ones, and then add them up. I think if you were really, you could do this big triangle because you know B and you know A, but we don't know that angle right there, so that would take some work to get. So I think your way is the better way. We have everything we need to find area of green and area of orange, so I think I would just do that. 1/2 AB, sine of the angle between them. Oh, this is a good one because be careful. you have all three sides. If I'm going to use 120, which two sides should I use if I want to use the sine of 120? 6 and 10. So any two sides and the included angle. And 120 is the angle we know, so we should use the sides on either side of 120. So that area, 1/2, 6, 10, sine of 120, 0.5 times 6 times 10 times sine of 120, 25.98. Again, be careful, that's only one green triangle, so I'll need two of those, and I'll need two of the orange triangle. So the orange triangle, 1/2, again 6 and 10, and sine of 60, 0.5 times 6 times 10, sine of 60, is the same thing. Now that might seem weird. It will always be the case, though. There's a lot of geometry going on in the background there that makes those triangles that make those triangles have the same area. All right, so we got the orange, we got the green. So actually, we could just multiply one of those by 4 since they all happen to be the same. .923. Two oranges and two greens.
Are they always going to equal the same thing?
They are, because think back to the original area of a triangle. 1/2 base times height. So you don't have to find, like, look at the orange triangle and the green triangle. Wherever that height is that makes a right angle, they have the same base, right? The orange base is here, the green base is here, and they have the same height, so they'll have the same area, even though they look very different. So that's kind of weird, but they will always be the same. If you believe me that they'll always be the same, then you can only find the area of one of them and multiply by 4. If you think I'm crazy and you want to find both of the areas and add them up that way, that works too. But no, it's not a fluke that this one were the same. It will always be that they're the same.